Okay, so now we're going to go through and look at a bunch of different types of reaction mechanisms. And then again, at the end, we're going to like consider, well, what occurs when and all that good stuff. But for now, we're going to look at each one of these individually. The first one is what's called an SN2 reaction. So what the heck does that mean? Well, so first of all, the S refers to substitution. So now we're specifically talking about substitution reactions, not elimination reactions. Nonetheless, if an alkyl halide can undergo two different types of substitution reactions. One where the mechanism is concerted and one where it's stepwise. So SN2, we're going to focus specifically on the concerted mechanism. So what do I mean by concerted? By concerted, I mean that the nucleophile is going to attack that electrophilic carbon at the same time that that leaving group, that halogen, is lost. So this is what I mean by concerted. These two things happen in the same step. Again, we have nucleophilic attack occurring at the same time as loss of a leaving group. So this will lead to a substitution reaction, and again, it's in a concerted type mechanism. So again, drawing the mechanisms, super important, right? So what am I going to do given this sort of set of reactants here? I'm going to make sure to draw my nucleophile attacking that electrophilic carbon in the same step as that leaving group is lost. Nucleophilic attack, loss of leaving group happen at the same time. That is what characterizes an SN2 reaction. Just to pick this apart, S is because it's substitution. The N refers to the fact that it's a nucleophilic substitution, right? We have a nucleophile attacking, that's what's leading to the substitution. The 2 is because it's bimolecular. Whoops, bimolecular. What do I mean by that? It means that both species, both the nucleophile, right, this is our nucleophile, and the alkyl halide, both of those are involved in the first step, or really the rate limiting step of this reaction, right? Both of those species, because the nucleophile is attacking in the same step that that leaving group is being lost, both of those guys are playing an important role. So that's where that 2 comes from. A really common point of confusion is to think that the 2 refers to the number of steps. This is going to be one step, right? So SN2 is actually only a 1-step reaction. In terms of the rate, this is really where the bi comes from. You have some constant times the concentration of nucleophile times the concentration of alkyl halide. Right, that's really what that 2 comes from, is both of these species, both the nucleophile and the alkyl halide, are important for determining the rate of this reaction. Okay, so now we're going to just like sit here and talk about SN2 reactions for a while, all the different factors that you have to consider. The first is stereochemistry, right? There's a reason why we learned about a bunch of stereochemistry before getting to reactions, and that's because certain reactions have different stereochemical implications. In an SN2 mechanism, we will see an inversion of our stereochemistry, right? So over here, our reactant has S stereochemistry, our product has R stereochemistry. I just want to note, it may be that both reactants and products have, for example, S stereochemistry because of the way that the groups are numbered. So for example, this is a high priority group and it's being replaced by a high priority group. So that's really why we see it go from S to R. So it's not necessarily that simple. You got to look at the actual product to figure out, do your priority counting, all that good stuff, to figure out what it's going to be. Nonetheless, this is what we call a stereoselective reaction because only one of the stereoisomers is produced. And the reason is because when your nucleophile attacks, it has to attack from the back, right? It can't go over and hit this front side here because the bromine's in the way. So you're going to have what's called an inversion. And again, by inversion, I don't necessarily mean it goes from R to S. I mean that the molecule actually kind of like flips. Like think of what happens to an umbrella in a really windy day, right? If your umbrella is all, you know, keeping you dry, and then all of a sudden the wind goes and it pops up the other way, it inverts. That's what we mean by a stereochemical inversion here. You can sort of explain this using the electron density. I don't know, HOMOs and LUMOs are a little bit of a hard thing to picture. I think more importantly though, just think in terms of electron density. The bottom line is that the halogen is going to have this big partial negative charge sticking up off of it, right? Which means that a nucleophile, which also has that pair of electron, nucleophile is an electron-rich species, it's not going to have an easy time approaching that halogen. Likewise, because you have this carbon-halogen bond, right? We said that carbon's electrophilic. That means that there's a partial positive charge over here. So the nucleophile will have an easy time approaching from that back side. So this is what we call a backside attack. Okay, and again, important, this leads to like a flip or a pop. And so if we want to sort of, well, so first of all, again, let's just make sure we're good about the fact that this nucleophile is going to attack in the same step that that electrophile is going to be lost, right? That's an important aspect of this. But now let's think about what the transition state would actually look like. Remember, your transition state in terms of our free energy, this is reaction coordinates. It's going to be that point right here at the very top of that energy landscape, where things are quite frankly the least, you know, it's the most unstable portion of this whole curve here. And this is where the bonds are being half broken and half formed, right? So this bromine carbon bond is going to be half broken, and this newly formed nucleophile carbon bond is going to be half formed. And so if I wanted to draw that, here's my carbon. We draw that with these dotted lines. Right? So this would be what my half formed, half broken lines look like. Again, I guess I can be good about color coding here. But equally as important is what happens to these other groups. Notice how the methyl group is sort of sticking out towards you, of course, because it's in that dash structure, but it's kind of pointed over towards the left, right? And then on my product side, it's over towards the right. That's because, again, of this inversion. So this transition state, not only does it have these half broken, half formed bonds, but it also has your methyl group, your ethyl group, and your hydrogen all lying in the same plane, okay? So this is a tetrahedral, this is a tetrahedral, but here, all these atoms that are in green are actually all in the same plane in our transition state. So again, think about it as an umbrella in a windy day. It's really going to invert during these reactions. It's something that's specific to an SN2 reaction, is this stereochemistry inversion.